Okay, so when I look at 18, I've got sine of x plus cosine squared of x over sine of x. So normally the first thing that I would think I would want to do is move sine of x to the numerator. But if I did that, let's think through what would happen. Sine up top would become cosecant. Well, do I know anything about cosines and cosecants? No, that's not going to do me any good. So my first instinct here was wrong. It doesn't make any sense for what it's going to do in the end. So the next thing I think of is, okay, well, this is a fraction, and I'm adding. So when I add fractions, I can get a common denominator. So that's the next route I'm going to go and think through that. So if I get a common denominator, they both need to be over sine of x. Okay, so how did I get from 1 to sine of x? I had to multiply by sine of x, which means I have to multiply the numerator by sine of x. So now in the numerator I have sine of x times sine of x, which is sine squared of x. And then the other fraction already had a denominator of sine of x, so it just stays as cosine squared of x. Now when you write fractions like that with a common denominator, we can write it over a single denominator like this. And so up in the numerator, I have sine squared of x plus cosine squared of x. It sure does. So my Pythagorean identity, sine squared plus cosine squared, is the same thing as 1 over sine of x. And then we don't normally like to have the trig function in the denominator as my answer. So I'm going to move that to the numerator. Sine to the numerator becomes cosecant. So my final answer for 18 is cosecant of x. Okay, and then 19. First thing I noticed, this cosine has a negative argument. So I need to fix that first. So when I have a negative in the argument, I pull it out front. Well, for cosine, we just drop it, right? It just becomes a positive. So this is 1 over 1 plus cosine of x plus 1 over 1 minus cosine of x. And so I would go through that same logic that I had before. So I'm adding fractions, so I probably want to get a common denominator in order to do that. So to get a common denominator, I'm going to multiply this fraction by 1 minus cosine of x on top and bottom. And I'm going to multiply the second fraction by 1 plus cosine of x. So I'm multiplying the denominators by each other. So now in the denominator, I'm going to have 1 minus cosine of x times 1 plus cosine of x for both of those. That is my common denominator. And then in the numerator, I'm going to have 1 minus cosine of x plus 1 plus cosine of x. Because when I multiply this out times 1, it just leaves me with that. When I multiply this by 1, it just leaves me with this. Okay, so looking in the numerator, I have 1 plus 1, which is going to be 2, and then I have a negative cosine plus a cosine. So those cancel out. Now my common denominator there looks like it's something that's been factored. So I'm going to distribute. So I get 1 times 1, which is 1. 1 plus cosine of x minus cosine of x times 1. So those two middle terms are going to cancel. A positive cosine and a negative cosine. And then I've got negative cosine times positive cosine. That's going to be negative cosine squared of x. So now in the denominator, that looks like the makings of a Pythagorean identity. So I'm going to look at my sine squared plus cosine squared equals 1 identity. Can I make it say 1 minus cosine squared? I can if I move that over. So that's going to give me sine squared equals 1 minus cosine squared. So I substitute in. That's going to give me 2 over sine squared of x. And now if I move sine to the numerator, it becomes cosecant. So that's going to give me 2 cosecant squared of x. So these are kind of similar to some things that we've done already. In each exercise, use identities to find the exact values at alpha for the remaining 5 trigonometric functions. So 20, it tells me sine of alpha equals 3 over 4, and alpha is between pi over 2 and pi. Okay, so that second part, alpha being between pi over 2 and pi, that tells me what quadrant I'm going to be in. So if I'm between pi over 2 and pi, that means I'm going to be in the second quadrant. So here is the central angle, so we'll call that alpha. Sine is the opposite over the hypotenuse. So my opposite is 3, my hypotenuse is 4. Now I can find my missing side by using the Pythagorean theorem. I know the hypotenuse in a leg, I'm missing another leg. So I'm thinking 3 squared plus the leg squared, so I'm going to go x squared equals 4 squared. So that's going to be x squared is equal to 16 minus 9. So x squared is 7. So that means that x is going to be the square root of 7. So my missing side there was radical 7. Now I'm in the second quadrant, which means sine and its reciprocal. So sine and cosecant are the only things that will be positive. All my others will be negative. So as I'm filling this out, I know sine of alpha is 3 over 4. So next, cosine of alpha is going to be negative. Cosine is the adjacent over the hypotenuse. So it's going to be negative radical 7 over 4. Tangent of alpha, again in the second quadrant, is going to be negative. Tangent is the opposite over the adjacent. And then if I rationalize that, that's going to be negative 3 radical 7 over 7. Okay, then we go with the reciprocals. So I've got the reciprocal of sine is cosecant, so it's going to be positive. If sine was 3 over 4, cosecant is 4 over 3. The reciprocal of cosine is secant. So cosine was negative, so secant is going to be negative. And I've got negative radical 7 over 4, so that's going to be negative 4 over radical 7. Then we have to rationalize that, so that's going to be negative 4 radical 7 over 7. And then cotangent, okay, because tangent was negative, cotangent's also negative. And then it's just going to be the reciprocal. So I'm going to flip this one before I rationalized it. So it's going to be negative radical 7 over 3. Because we can't have a radical in the denominator. We have to rationalize it. So like in your calculator, if you put 3 over radical 7, I think it'll do it for you. But what you have to do, you have to multiply top and bottom by radical 7. Is how you rationalize. So that just becomes negative 3 radical 7 over 7. Any other questions on 20? Okay, so I'm looking at 21. Cosine of alpha is negative radical 3 over 5, and alpha is in quadrant 3. So this time they just tell me what quadrant I'm in. So I'm in quadrant 3. Right, here's my central angle alpha. Cosine is the adjacent over the hypotenuse, which means my adjacent side is radical 3, my hypotenuse is 5. I can find the missing leg by using the Pythagorean theorem. So I'm going to have radical 3 squared plus the other leg squared equals 5 squared. So when I solve that out, that's going to be x squared equals 25 minus 3, which means x squared is equal to 22, which means my missing side there is radical 22, which does not simplify. Okay, so I know cosine, so when I'm finding my other trig functions, I'm in the third quadrant, so only tangent and cotangent will be positive. Everything else will be negative. So I would say sine of alpha. Sine is going to be the opposite over the hypotenuse, and again that's negative because I'm in the third quadrant. We know cosine, so I would go tangent. Okay, tangent's going to be positive. Tangent is the opposite, so radical 22 over the adjacent, which is radical 3. So now when I multiply top and bottom by radical 3, that's going to be radical 66 over 3. Let's see if 66 will reduce. It doesn't with 4, it doesn't with 9, it doesn't with 16, it doesn't with 25, it doesn't with 36. So no, that will not simplify. And again, it's positive because I'm in the third quadrant. Okay, so now we start working with the reciprocals. So the reciprocal of sine is cosecant. So cosecant would be negative 5 over radical 22. And so when I multiply top and bottom by radical 22, that's negative 5 radical 22 over 22. My final answer for cosecant. Okay, next I'm going to look at secant. So I know cosine is negative radical 3 over 5. So that means secant is going to be negative 5 over radical 3. Then when I rationalize, that's negative 5 radical 3 over 3. Okay, then the last one here is cotangent. So I'm going to flip the original before I rationalized. So it's going to give me radical 3 over radical 22. So I'm going to multiply top and bottom by radical 22. That's going to give me radical 66 over 22. Okay, so this is starting to transition us to the sort of problems we're going to have in the next section. It's not quite, but it's a beginning. So it tells me to write an identity that expresses the first function in terms of the second. So I have cotangent of x, and I want to write it in terms of cosecant of x, which means the only trig function that I can have in my final answer is cosecant. I don't want any other trig functions. So I'm starting with cotangent, and I'm going to manipulate it until I make it say cosecant. I'll say, okay, oh gosh. I'll say, can you see? So cotangent is cosine over sine. So this is going to be cosine of x over sine of x. Okay, so if I move sine to the numerator, it's going to become cosecant. So now I'm going to have cosine of x cosecant of x. So the cosecant part is good. That's what I want. But now I've got to manipulate this cosine. So if I can make cosine into something that looks like sine, I know I can convert sine to cosecant by swapping it from the numerator to the denominator. So the trig identity that works with cosine and sine would be the Pythagorean identity. Sine squared plus cosine squared equals 1. So this is a little scratch work over here on the side. I know sine squared plus cosine squared equals 1 because it can turn cosines into sines. So now all I want is a regular cosine. So I need to solve this for cosine. So that's going to be cosine squared equals 1 minus sine squared. And then to get rid of the squared, I have to take a square root. So that's going to tell me cosine is equal to the square root of 1 minus sine squared. Is that really going to help? Let's think.
You know, there's an identity that has cotangent and cosecant and they call themselves.
Well, let's try that.
Plus cotangent squared of x equals cosecant.
So one of the Pythagorean identities?
And you end up with radical cosecant squared of x minus 1 is the answer.
That sounds much better.
Now I believe you that you don't have them memorized then.
I don't have them memorized. No, I can discover them. That's the rule. I showed them how in the video, how I go from this to the other ones. I have that one memorized. So if I'm dealing with cotangent, cotangent is cosine over sine. So I need to divide everything by sine squared. No, that's what I just did. That's what's going to happen a lot if you work these. You'll think you're going down one path, just because we're eventually going to start looking at, we're going to be given something and we're going to be told what it has to look like in the end. So it's one side equals another. And so then you have to work on one side until you make it match the other side. And so you can think I'm supposed to be doing this and then do the wrong thing and have to go back and go back. So what you're seeing is me really doing it. I'm not sitting here with notes. This would be my real process. I'd have to go through it. The reason that I knew that first way wasn't going to work, once I plugged in here, it was going to have sine in it in a radical. So I can't just move the whole thing to the denominator because the radical would change its power from a half to negative a half, but then that wouldn't change anything on the inside. So I knew I was stuck, that there was something that was going to be wrong there. But now if I look at this 1 plus cotangent squared equals cosecant squared. So now if I don't do that, so now let's solve for cotangent in terms of cosecant. So I'd move the 1 over, it would become negative. So I've got cotangent squared equals cosecant squared minus 1. Then take a square root. So cotangent is going to be equal to plus or minus the square root of cosecant squared minus 1. So now I can substitute in. Cotangent is just the same thing as plus or minus the square root of cosecant squared minus 1. Final answer. Okay, so if I'm writing secant in terms of tangent, okay, so sine squared plus cosine squared equals 1. If I'm having to do with tangent, tangent is sine over cosine, so I'm going to divide everything by cosine squared. And again, this is just how I get to the other trig identities, or the other Pythagorean identities. If you don't want to do it that way, you can just memorize them, which would have probably served me well if I'd have done that when I was in school. But hey, I'm lazy. So, now I've got secant, and I want to rewrite it in terms of tangent. So secant squared is already isolated, so I would take a square root of both sides. So that's going to tell me secant equals plus or minus the square root of tangent squared minus 1, plus 1. And so I'd substitute that in. That's plus or minus the square root of tangent squared of x plus 1. Okay. So now we're finding cosine of the arc sine of x. And it tells me to find an equivalent algebraic expression for each composition. So if you'll remember, we did problems kind of like this last chapter, where we had a trig function of an inverse trig function. And so we had to draw the triangle, figure out what quadrant we were in, do all that jazz. Okay, so for these, we're not as concerned with what quadrant we're in. We're just going to put them all in the first quadrant unless it tells us otherwise. But so this is where you have to remember what each thing is telling me. So arc sine or inverse sine takes a ratio of sides and is going to give an angle as an answer. So that means that x is a ratio of sides. Well, we don't have two sides, so we can put it over 1. So I have arc sine of x over 1 in the first quadrant. So I'm going to draw that out. So this is the angle that I'm looking for. So I'll put theta. Sine is the opposite over the hypotenuse. So my opposite is x, my hypotenuse is 1. Now I can find the missing side by using the Pythagorean theorem. So let's call this missing side, let me just put a for now. Okay, so that's going to be a squared plus x squared equals 1 squared. So when I solve that out, a squared equals 1 minus x squared. And then to solve for a, we take a square root. So a equals the square root of 1 minus x squared. Now we normally do plus or minus, but because it's a distance, we can just account for the positive. We can drop the negative. So that means my a here was the square root of 1 minus x squared. So now I have my triangle drawn with all of its sides. So I don't know what this is, but I know that my answer is some angle, right? That was the whole purpose. It gives an angle. So we're going to call it theta. So now what is cosine from that angle? So here from this angle theta, cosine is the adjacent over the hypotenuse. So cosine of that angle would be the square root of 1 minus x squared over 1. Let's look at another one similar. So cosine of the arc tangent of x. So again, we're just going to assume we're in the first quadrant. That arc tangent of x, that x is a ratio of sides. It's the opposite over the adjacent. So I can put it over 1, which means my adjacent side is 1. So when I draw this out, this is the angle I'm looking for, theta. Tangent is opposite over adjacent. So this time I'm missing the hypotenuse. So I could say 1 squared plus x squared equals the hypotenuse squared. Take a square root of both sides. That means the hypotenuse is the square root of 1 plus x squared. So I know my missing side is the square root of 1 plus x squared. So now our tangent of x, remember that's just going to be some angle theta. And so now I'm finding cosine of that same angle. So cosine would be the adjacent over the hypotenuse. So that's going to give me 1 over the square root of 1 plus x squared. Now I have to rationalize this, so I have to multiply top and bottom by square root of 1 plus x squared. So that's going to be the square root of 1 plus x squared over 1 plus x squared. Okay, so quick review of functions. If I plug in a negative and I get what I started with, then I can say the function is even. If I plug in a negative and it changes the sign of everything, then I can say the function is odd. If neither one of those things happen, then it's neither. Okay, so right here we're going to plug in a negative beta. So this becomes 1 plus cosecant of negative beta. So now we're looking at our even and odd identities. So cosecant is the reciprocal of sine. If I have a negative inside a sine, it comes out front. So the same thing happens with cosecant. So this is 1 minus cosecant of beta. So when I plugged in a negative, did it keep all of the signs the same? No, it changed this one. When I plugged in the negative, did it change all the signs? It changed this one, but it didn't change that one. So neither thing happened. So my answer here would be neither. That's neither even nor odd. Okay, so for 27, we're going to be plugging in f of negative x. So that's going to be sine of negative x. Oh, no. F of negative x is going to be sine of negative x over negative x. So now the negative on the inside for sine comes out front as a negative. So it's going to be negative sine x over negative x. Well, now I have a negative divided by a negative, which is a positive. So that just leaves me with sine of x over x. So when I plugged in negatives, I got back exactly what I started with. So that is an even function. So I could say 27 is even. Okay, now 28. If I'm looking at f of negative x, that's going to be equal to negative x times cosine of negative x. Now, when I had a negative on the inside with cosine, it just goes away. When I pull it out front, it doesn't do anything. So that is going to be negative x cosine of x. And so when I plugged in my negatives, it changed the sign of everything. Right? Because this is just one term that was positive. Now that one term is negative. So it changed the sign of everything. So we could say that this is an odd function.